Hello, everybody. Thanks for coming today. So, myself, Ryan, and Sharad, we are both engineers at NerdWallet, and we're going to be talking about how Amazon SageMaker helped us build a machine learning platform with 3 engineers. So, before we get too far into the talk, some of the key takeaways that we want you to take away today are how we run our ML engineering projects at NerdWallet, how we structure our teams at NerdWallet, and some of the best practices we've learned along the way. We're also going to be diving deeper into how we learn to be a bit more productive with limited resources in terms of people at NerdWallet. And then we're going to dive into why we chose Amazon SageMaker and why we found it's been incredibly flexible for us so far. And we're going to dive a little bit deeper into how we use the Amazon SageMaker build your own container feature and how it helped us build a human-centric ML workflow. So here's the agenda for the talk. First, we're going to go into the why build an ML platform, some of the guiding principles, some of the technology choices, like why SageMaker. Then we're going to go into the what and how. So what do we enable with this machine learning platform at NerdWallet? What it is really, what is it, what does it do? And finally, some of the guiding principles in action that we talked about earlier in the talk with some of the architecture constraints. And then finally, we're going to reflect. What are some of the things that we learned? And what's coming next for ML platform at NerdWallet? Quick caveat, this is one way of building a machine learning platform. It's certainly not the only way, but it's given us kind of what we've wanted so far. And we're going to talk about the development experience, specifically model training, and we'll be happy to take questions at the end if you have any. So, pretty famous guy. He said, "If I've seen further, it's by standing upon the shoulders of giants. Discovered gravity, Isaac Newton." So here's the giants, and here's some of the shoulders that we stood on when we were thinking about and building ML platform. So Netflix has a product called Metaflow. Uber has a very famous product called Michelangelo. There's also another extension of that called Michelangelo PyML. And finally, Databricks has a product called MLflow. So there's a lot of good content out there. We read through a lot of the talks and the blog posts that these companies have produced, and we drew a lot of inspiration when we were thinking about and designing this system. So first up, why build an ML platform? So quickly, we're going to look at machine learning at NerdWallet. Why do we need machine learning at all? Then we're going to dive into why build an ML platform. And again, we're going to look at the guiding principles and then why SageMaker. First up, why do we need machine learning at NerdWallet? So for those of you who don't know what NerdWallet is, think of it kind of like Yelp for personal finance, with the long-term vision of being sort of like an automated financial advisor, if you will. So the first use case, quick pop quiz. Who here has applied for a credit card? Alrighty, that was an easy one. Who's been rejected for a credit card now? Okay, so have I. So I'm originally from Australia. When I first moved over to America, thought I had a pretty good credit score, went to apply for a credit card, and I was rejected. So that was a subpar experience. And one of the things that NerdWallet's able to do is you're able to sign up, you get a credit score, link your bank accounts, your credit card accounts, etc. Using that information, we're actually able to provide a better user experience where we're kind of able to help predict whether you're likely to be approved for a financial product. So that's one key use case for machine learning at NerdWallet. The second one is we actually have a huge amount of content at NerdWallet. We have something on the order of 16,000 blog posts about a huge different variety of financial literacy topics and sort of personal finance topics. So if we're able to more accurately match users with the content that they're coming to NerdWallet for, we're able to provide a much better user experience in general and hopefully help folks further their personal finance journey. So let's dive into why build an ML platform. So before we had a machine learning platform at NerdWallet, it took months to ship a model. So data science was siloed from the ML engineering team, and we were operating with a kind of scrappy, get-it-done type attitude. Some of the challenges we ran into were, if you're building a data science model, how do you generate the data that feeds into the model? So we had things like data scientists writing manual SQL queries, and then you run into things like data scientists, if they don't have a standard way of accessing compute resources, they have to spin up compute resources via Amazon. That means that they're having to run sort of an upper bound of the compute resources that they need. So it's often more expensive than it needs to be. And then there's the obvious challenge of data science at most companies, which is like manual developer environment management. So then we get into the handoff process. Now, if there's one thing that we've all learned in software engineering, it's that waterfall development is the optimal way to develop software. That's a joke. It's certainly not the optimal way. A bit more of an agile process is certainly going to be more effective. So some of the challenges we ran into were release engineering a model. Small bugs were leading to large headaches. So things like library version mismatches. Maybe in training, we were using scikit version X, and in production, we were trying to use scikit version X+1. Things don't match up. We had other challenges around data shape mismatch. So in training, perhaps you had a float for one particular feature. In production, it's coming across as an integer, and your predictions are completely out of whack. And things like retraining. When retraining needs to happen for a model, whose responsibility is it to sort of generate the retrained model? How do we do the handoff between data science and ML engineering? How do we retest? How do we get sign-off from product managers that the new results from the retrained model are effective, et cetera? So the summary is there was a large cycle time between data science and ML engineering, and we often weren't on the same page. And this is the information flow before we had machine learning platform. You can notice again that earlier I mentioned it was a bit waterfall-y. So we've stratified this into 3 layers. We've got the data science layer, the ML engineering layer, and then the product layer, so product manager. And you notice that it's sort of very unidirectional. So to get to a point where a product manager is able to view the results of a model, it's often at a point where the model is already in production. Now, if anybody's read Fred Brooks's The Mythical Man Month, I think he has a section in there where he talks about the cost of changing something at the design is 10 times cheaper than the cost of changing something at implementation time, which is 10 times cheaper than changing something at the cost of QA, and then finally 10 times cheaper than production. And so if you look at this sort of information flow and workflow, it often became quite expensive to change a model because by the time we'd already got all the way through to production, the cycle time could be sort of weeks or months. So why ML platform? Getting it done wasn't really helping us get things done in the long term. The handoff, as we mentioned, led to non-ideal ownership issues. So the model's down in production. Whose responsibility is that to fix? Is it a data scientist, an ML engineer? What does that look like? We talked about the model needing to be retrained, unclear ownership there. And the model being in production doesn't necessarily mean it's being signed off by a product manager. So there's still work remaining, and it's not quite a sort of clean separation of concerns. And we talked about data scientists having to wear too many hats. So data scientists are experts at the science piece, but it's probably not the highest value use of their time for them to be configuring AWS compute resources, for example. So we wanted to take that complexity away. Having to worry about sort of managing library versions and shared resources was a suboptimal experience as well. And finally, worrying about things like trying to automate parts of this process by writing custom makefiles was not an optimal use of data scientist time. So we looked at this and we said, what if we could solve 80% of these problems with just better tooling? This graphic is from a paper released, I think in 2015 by Google, called Hidden Technical Debt in Machine Learning Systems. It's a very good paper. I totally recommend a read. But the blurb here is quite interesting. So it says only a small fraction of real-world ML systems is composed of ML code itself. This tiny little black box in the middle. The remaining surrounding infrastructure is vast and complex, and it can be thought of as engineering plumbing. And so we're not saying that we solve all of these sort of surrounding engineering plumbing problems, but what we are saying is that there's generally a fairly small amount of data science code relative to the amount of work required to fully productionize a machine learning model at a company today. So there was a talk by a fellow called Brian Galvin of Netflix, and he identified 3 key sources of friction that data scientists often face at companies. So those were scaling beyond a laptop. If you need more than 12 cores to train on like a standard MacBook Pro, how do you get access to that? Reproducing results. How do I make sure that I use the same data to train the model? How do I make sure that I use the same versions of libraries, et cetera? And finally, going to production. How do we host models? How does scheduled retraining work? How do things like monitoring of models in production work? So we looked at these sources of friction, and we realized that we were facing many of the same sources of friction, or all of those 3. So we came up with a design goal for ML platform. And that was ML Platform's goal is to solve the plumbing problems of a real-world ML system by removing the friction of scaling beyond a laptop, reproducing results, and going to production. And that led to what ML Platform's going to do. So the machine learning platform will provide a platform for data scientists to develop, train, deploy, and monitor machine learning models. And the aim of ML Platform is to drastically reduce the time required to develop, train, deploy, and monitor those models by solving the common sources of friction, those three common sources of friction that we just mentioned. And the idea is this will enable our data scientists to achieve their goals faster, and ultimately, we as a company will be able to achieve our business goals faster. And just a quick review of the stakeholders. So the title of this talk mentions 3 engineers, but the reality is there's quite a large surface area, quite a number of people involved in machine learning at companies today. So a quick overview, there's folks like data analysts, data engineers, data scientists, DevOps engineers, machine learning engineers, product engineers, and product managers, of course. So it really takes a village to ship a machine learning model to production. And let's have a quick look at some guiding principles. So what we wanted and some of the design principles that we placed on ourselves. So some of the system design principles we went for are, we wanted to remove friction, so those 3 sources of friction, scaling beyond a laptop, etc. We wanted to make it easy to do the right thing, and we wanted to make it difficult to do the wrong thing. And finally, and this is a key part of the talk, wherever possible, we wanted to leverage existing solutions. We have a limited number of people, and we want to achieve a lot. So we have to be intelligent about the technology choices that we make. So this led to the architecture constraints. So the architecture, we said, will rely as much as possible on Amazon managed components. So for training, this means we'll offload as much of the heavy lifting as possible to Amazon SageMaker. For workflow management and scheduled jobs, the architecture will build on top of Apache Airflow. And for building and deploying packages to production, we have an internal build deploy system called Indy. And so a key part of this is we wanted to integrate with our existing build deploy system so that we were able to sort of leverage a lot of the work that's already been done internally to make it easy for folks to build and deploy models to production. And then the key point in general is we wanted to avoid reinventing the wheel as much as possible. So very quickly, why Amazon SageMaker? So at NerdWallet, we're an unabashed AWS shop, which basically means all of our infrastructure is AWS. And that means it's a very attractive option because we have a lot of the infrastructure built out to make use of all of the tools and systems that AWS provides. So we thought of Amazon SageMaker as ML compute as a service. And when we looked at some of the Amazon-based alternatives, we came up with 2. Amazon Batch is probably the primary alternative. One of the challenges with Amazon Batch is it's kind of a step down from SageMaker in terms of being custom built for machine learning. So one of the key pieces of SageMaker is, it might seem fairly simple, but having a fairly slick UI to look at the compute resources, things like metrics like CPU, memory usage, GPU usage over time, can be super important for helping data scientists debug things like, why is my model taking so long to train? Why am I only using 10% of compute resources on this machine with 96 vCPUs, for example? Secondary alternative, this might look a little bit odd here, is Amazon ECS. So the reason that we considered this is we use Amazon ECS for our current apps cluster. So for deploying standard backend services, ECS has been particularly effective for us. The challenge with data science is we want a heterogeneous collection of compute resources. So one model might require a lot of CPU. Another model, like a neural net, might require a GPU. So doing heterogeneous collections of compute resources just isn't as effective as using SageMaker when compared with Amazon ECS. Quick fun fact. So in 2008, IBM delivered the Roadrunner supercomputer to the US Department of Energy. Now this supercomputer was for something like modeling the decay of the US nuclear arsenal. The cool part is the performance of this supercomputer was 1 petaflop. And at the time, it was the most powerful supercomputer in the world, the first to break 1 petaflop of sustained compute performance. Fast forward to 2019, you can rent 1 petaflop of computing performance, specifically the MLP316X large, 8 Tesla V100 GPUs. 1 petaflop of computing performance $34 an hour. So choosing SageMaker means that you get to build, like stand on the shoulders of giants in terms of taking advantage of all of the latest advances in hardware. And as you saw from the keynote this morning, there's a massive number of sort of new features constantly being released. Some quick learnings about how we work. So cross-functional teams rather than handoffs across teams. Try and co-locate the folks who will be working on the project together. And so for us, this meant 2 machine learning engineers and a DevOps engineer. And then in general, try and minimize feedback time and optimize for learning and iterating as rapidly as possible. Pretty standard key agile principles, but it was fairly effective when we went about sort of designing and implementing this project. And now I'm going to hand it over to Sharad to tell us a little bit more about what we built.
Thanks, Ryan. Cool. So we've seen why we built the ML platform. In this section, we'll see what did we enable and what did we actually end up building, right? So what is the data scientist development experience like? What is ML platform? What's the tech stack? What do we use? How do we build this? And how do we sort of map that back to the guiding principles that Ryan spoke about? So let's start off with what we enable. Now, I'm going to take you through what our data scientists do when they want to start a new ML project. We call them ML pipelines. That's standard industry terminology. A new ML pipeline, we mentioned the Indy tooling that we have internally. That think of it as build deploy tooling that all engineers at NerdWallet use. And all they do is do this thing that says Indy new Python ML lib. You need to fill in a few standard details. What's the name of your project? What's the name of your Python module, and so on. And obviously, we're going to be using the Iris project because that's what all ML engineers need to use at a presentation. And they go in, they type in these few things, they press enter, and voila, they're done. What does that actually get us? It utilizes this open source project that you might have heard of called Cookie Cutter, and that's used for setting up these standard projects. And a standard project for us looks like this. At the top level, you have these various things that seem to have nothing to do with machine learning at all. You have a Jenkins file, you have a README, you have an ml.yaml, you have a version file. You have all these things, and all of these are essentially required for the platform to use the pipeline as this black box, right? So at the top level, we've already set up the repository in a manner that lets us use it in the platform, and that's the power of the cookie cutter. You also see that inside the actual source module, you see a model.py file. Now, who knows what's happening there, right? But the key here is standardization is great because, again, we have very few resources that we can dedicate to this. We're not a Netflix or a Google that can throw 100 or thousands of engineers at this, but we want the same things. We want the niceness that they have, but we can't afford to invest as much into it. So standardizing at this place, as we'll see later, helps us do a lot of help us essentially leverage economies of scale in a way. Now, the model.py file, if you've worked with machine learning, these seems fairly standard to you. There's some training code that you need to define. There's some save and load code that you need to define, and there's some batch prediction code, let's say, right? So standard implementations. Now, what's important to note here is that the machine learning engineer does not control any of this. It's all the data scientist who controls this. So the data scientist has this file. It's a stub file, but they can go in and they can start adding code to this. And we don't really care what the code is. All we care about is that it's implemented somewhere and that we know how to call it. So this is a setup.py file. It's one of the files that we saw at the top level, right? At the top level, you have the setup.py file. And let's dig into this because I said this is what the platform uses. Now, those of you who are familiar with the Python packaging ecosystem would have heard of this thing called setup tools. Python uses setup tools as a way to package and distribute projects. And one specific feature of setup tools is this thing called entry points. Now, entry points are pretty interesting because they let you use Python libraries or Python projects, but use them sort of like functions, like plugins. And what these entry points are going to be doing is, if you look at it as an equation, the LHS equal to the RHS, the LHS there is the left-hand side, the interface that the ML platform cares about. What the platform cares about is that the pipeline defines some way to load a model, to perform a batch prediction, to save, and to train. But what we don't care about, and what the data scientist cares about, is how it's implemented. right? So this is where the handoff happens. This is where we sort of leverage these patterns to delegate things to the pipeline itself, but the platform can sort of like delegate at key instances and work around that and provide a harness. And that's what happens here. NWML, I know that we spoke about the indie tooling. NWML is sort of NerdWallet machine learning. It's like our machine learning specific tooling that we provide to our data scientists, the same pattern, leverage a lot of the shared code that indie uses. And what it's going to do is it's going to start this local training. It's going to load the ml.train entry point that we saw on the previous slide. It's going to look inside these standardized data directories inside the structure of the project itself. It's going to load up that data, pass it to the entry point, get back that data, save it. Get back the model and save it, right? Very simple. And put that way, it's just a harness. It's a harness that delegates at various points to the actual implementation. Same thing goes for batch prediction. And before we jump into this, I'm going to pause here a little bit and talk about what have we enabled here, right? We've allowed data scientists to quickly create a new project and to super quickly iterate locally. And that's a fairly powerful thing for data scientists because they're used to having to SSH into these instances and pull down these large petabytes of data before they do something. Now, what we're telling them is, hey, you can do this on your local computer. You don't have to SSH anywhere. You can do this when you're on the move. You can do it anywhere you want. But probably don't download petabytes of data. Just take the top 10 rows or the top 100 rows. Sort of integration test your code before you do the expensive stuff where you spin up a server to do the computation, right? So the local development flow, and we referred to this a while earlier when we said human-centric flow, we're sort of enabling the data scientists to work on their own terms and not on the terms of the machines that they have to use to spin up these pipelines. So, but assume that the data scientist has done this. They've added some code, they've run through it with like a sample data set. It's fairly easy, and they're feeling confident. They're like, okay, I want to actually run this thing now. They're going to open up a pull request. Now, most of you are thinking, why? Like, what does this have anything to do with a pull request? And the reason we open up a pull request is we use GitHub internally for our version control, and a pull request is a nice unit of work that we use to share code. And the other interesting aspect of a pull request is it gets plugged into these continuous integration checks that spin up and do these various things. It runs integration tests, it builds these artifacts, it builds documentation, all of those things. And for an ML pipeline, what it's specifically going to do is that it's going to build a code artifact and ask the ML platform to start training on SageMaker. So this is how we're sort of plugging into existing CI hooks and adding a special hook for this kind of a project where we use the resultant code artifact on SageMaker. And the way that's going to look for the data scientist is they open up a pull request and they get a comment back on the pull request that says, hey, we have a training job that's been kicked off for this project. And every time they push up a commit, a new artifact gets built, a new training job gets triggered, and you get all these details. It's really important here to note that we don't want to build a UI for this. Like Ryan said, SageMaker has an awesome UI. We don't want to reinvent that wheel. What we will do is provide this ease of linking to the exact job in the UI, something that's easy for them to understand instead of going in, searching through the logs, and searching for the exact job that we spun up. Since they're not spinning up the job, we need to tell them where to go find it. Those of you who have used SageMaker are probably looking at me really cautiously and skeptically saying, but how do you get the data? How do you know what to use to spin up the training job? And that's where this comes in. Another of the files that we saw at the top level that the platform uses is an ml.yaml file. It's also part of the interface between the pipeline and the platform. Specifically, you'll see that we talk about things like resources and instance types and input data files and where to go find it on S3. And this sort of gets to the heart of what we're doing. What we've enabled is version models. Since to spin up a training job, you need to open up a PR, which goes through CI, which goes through model artifact generation. Code artifact generation. What we have done is versioned models and versioned pipelines. At no point will the data scientist say, oh, I had this pipeline, I have this model from the pipeline, I don't know the code that generated it, because everything is tied back. A model is tied to a training job that's tied to a code artifact that's tied to a SHA hash on GitHub. right? So everything is reproducible, and we also do reproducible data sets on the way. Smoother development, like I spoke about, I don't want to touch too much on it anymore. It's the local training and how the ease of doing local training before you need to use remote instances. It's super clear ownership. There is no handoff. In production, we use the same model that was trained by the job that the data scientist kicked off. We never re-implement the model because that leads to too many ownership issues. We use the mental model that the scientist owns the entire model. We own the entire plumbing. If something goes wrong and they can't trigger a training job, but they can't pull up a model, that's our problem. But otherwise, the scientist knows that they have to go debug and they completely own this. It's their code that's running. And really nice things like economies of scale. We could build the platform because it makes sense to do for multiple projects. We can do things like Slack notifications. We can do things like cost management. We can do all these value-added services that don't make sense for a single pipeline, but make a lot of sense if you do it across multiple pipelines. Now that we've seen the spiel about what we enabled, let's actually look at the details of what we built. Quick recap, what does ML train do? It does this harness. It loads the installed entry points. It does model training using standard data locations and a standard interface. And it does model saving in much the same way. And what does a git push do essentially? The exact same thing, but it runs on SageMaker and uses data on S3. It's a super simple mental model. There's nothing complicated going on here, at least from the data scientist perspective. They push up the code. Exact same thing that's happening locally happens there. If there's an error in the remote training job, they can reproduce it locally, right? And that's a powerful mental model for them to have. Of course, it's not this simple. This is what it actually looks like. Now, there's a bunch of boxes here, so I'm going to quickly run through the logos and come back to this slide. The various things that we use are GitHub for part of the UI. Essentially, we didn't rebuild the UI. We also use Slack for a similar case. And they have the CLI tool as well. We use Jenkins internally for continuous integration tests and continuous deployment. So Jenkins is the one that's building these code artifacts. Flask is a very popular Python web framework. We use that as for a live service that does metadata management. Data scientists want to know what the status of their job is. They don't want to hit the SageMaker API. We sort of wrapped up into an API here. We use a scheduler, that's Airflow down there, the fan. Then, of course, we use SageMaker and we use Artifactory and S3. Now, armed with that information, let's see what happens here. Git push triggers a Jenkins CI job that tells essentially our orchestrator or our metadata manager that, hey, we need to trigger a training job for this pipeline. Now that goes back and comments on GitHub, and it also performs orchestration with Airflow, which in turn triggers a job on SageMaker. Probably wondering, why is Airflow involved here? The reason is training jobs either are triggered ad hoc for exploration or on a scheduled for productionalization, right? And we want a consistent interface between them, so we use Airflow for both the ad hoc case and the scheduled case. And then the data comes from S3, and the model artifact goes back into Artifactory. Now, why does what I say, how does it map to what Ryan said earlier about guiding principles? The two key pieces here, there are many pieces that we can dig into. The two key pieces are why we used Airflow, and even more importantly, why did we use a specific feature of SageMaker called build your own containers. Airflow, it's almost a no-brainer. There are some alternatives, like something like AWS Step Functions does a similar thing. But the key piece here is a super strong community. Airflow is an open source project now. It's now Apache Airflow. Very strong community, data engineering people love it, and that's key actually. We used it because a lot of ML engineering has overlap with data engineering, and there are going to be these it's going to be smart to have these tight synergies between them. Since our data engineering team already defines data dependencies and pipelines in Airflow, it made sense for us to sort of piggyback off of that and use Airflow for our scheduling as well. It's a very typical use case that something happens on the data side, and that triggers a training job. But more interestingly, why did we use this specific feature of SageMaker? Why did we build our own containers and our own code artifacts? Doesn't SageMaker give us these optimized training algorithms? Now, the key piece here is we really, really wanted to enable that local development flow. And local development with SageMaker isn't as seamless as we would have liked it to be. The other part of it was that it was really easy for us internally to build containers. We had a lot of tooling, all of our back-end apps, all of our front-end apps, everything builds containers and builds images and deploys containers. Now, by combining these two, SageMaker has this cool features which says, as long as your container defines an entry point that can do training, you can use whatever container you want to perform training on SageMaker. We leverage that to say, okay, we're going to use our own containers, we're going to build our own images, and we're going to use our own containers for training on SageMaker, but we're going to leverage all of our existing engineering harnessing for building images so that we can enable the local development flow and also use SageMaker for the remote training instead of doing our own thing. So that's the key reason why we use the build your own containers feature and why it's sort of critical to how we do things in the ML platform. And with that, I will hand it back to Ryan to sort of reflect on what we learned.
Cheers. Okay, so what did we learn? There was a quote I heard one time which said there's two ways to learn things. One is via your own experience. The second way is via somebody else's experience, but it's much cheaper to learn from somebody else's experience. So, how we work today was one of our sort of key learnings that we're going to go into, and a couple more key learnings, and finally, we're going to look at what's next for ML platform at NerdWallet, what's on the roadmap. This is the same graph that we had earlier, but you'll notice that for this particular graph, we have a lot more loops now. So, as you saw Sharad demonstrating earlier, data scientist is able to run with a small subset of data locally. That means that they can start to show a product manager or an ML engineer the output of a model much earlier in the process. We're able to get these feedback loops going with all of the people involved in releasing a data science model to production before we finally get to production. So it's a lot cheaper. We're able to iterate a lot faster and move a lot faster in terms of delivering machine learning models to production. So we had kind of three key learnings. Handoffs between teams don't work as well as executing together. Co-locate folks, co-locate the work together, and it's going to be more effective. As we said earlier, avoid reinventing the wheel as much as possible, or buy rather than build, but preserve optionality. So one of the examples with preserving optionality is with SageMaker, we are using a lot of the functionality. We're not using 100% of the functionality, but we're also not locking ourselves into using a subset of SageMaker's functionality. For the new features that are released, we want to leverage them as quickly as possible to help make our data scientists even more productive. And a lot of the infrastructure and tooling that Sharad just spoke about is common across NerdWallet. So the advantage of this is we get to leverage the skills and experience of other engineers to help lean in on the project and help contribute to the project. And finally, we haven't listed it down here, but one of the points is you don't have to be a Netflix or an Uber, as we touched on earlier. You can kind of achieve this with a much smaller set of resources or a much more limited set of folks by making the right technology choices. And what's next? So obviously, scale out to more use cases. We have let's say the beginnings of data science models at NerdWallet. We have a lot of new use cases that we want to expand to. So things like business analytics, performance marketing, things like forecasting, et cetera, are key use cases for machine learning at NerdWallet. We want to automate setting up inference for the predictions that we produce. So both batch predictions and real-time inference. And some of the key pieces there, that may involve serverless in the future, especially given some of the announcements at reInvent this year. And finally, monitoring in production. We don't have a great story around monitoring models in production at the moment, so that's one area we're looking to improve. And things like automating health checks of a model, of a pipeline rather. So that's the general summary of what we're looking at next for machine learning platform at NerdWallet. And this talk will be released eventually on YouTube. These are a whole bunch of references that we had referred to earlier in the talk. So feel free to read through this at a later point. Don't worry about capturing it too much today. And in summary, we just wanted to say thank you very much for coming to the talk. It's been a pleasure speaking. Now, I think we have time for questions if folks are interested.
The announcements this morning on SageMaker Studio, do you anticipate any changes to your workflow and repeat the question?
Yeah, so the question was, given the announcements around SageMaker Studio this morning, do we anticipate any changes to our workflow? Maybe and hopefully. So I don't know yet, it was just released this morning, but the intent of building on top of SageMaker was being able to rapidly incorporate the new features that are released to sort of help make data scientists' life much more effective. Anything to add?
Yeah, the one thing I'll add is from a mental models standpoint, Ryan had this slide earlier from the Google paper where ML code was this tiny box and there was a large piece around it. We think of ourselves as a small shell around the ML code, not necessarily all the other things. So if Amazon is releasing things that do monitoring or analysis, for example, we'd love to just use that and have this small layer that adapts that for our use cases.
And the point in general is to basically, just like we are standing on the shoulder of the giants with the sort of architecture, we also want to rapidly incorporate the SageMaker stuff in general. Any other questions?
So the question was about feature extraction. We didn't speak about it, and the question specifically was, do we have any tooling that lets data scientists access common features, maybe a feature store or something of that sort? Right? So the answer is not yet. The reason for that is we're still sort of iterating, trying to figure out if a feature library makes more sense for our data scientists, where you share the code that does it, or a feature store makes more sense. A feature store is a heavy lift. It's a single point of failure. There's going to be high throughput on that store, and there's a cost associated with that. But it is a direction that we might go. Short answer is we are thinking about it. We do help them, but we sort of work with the data engineering team right now to generate these standard data sets. In terms of pushing that down to the pipeline, it's in the works, but TBD how we do it. Did that answer the question? No worries. Yep. So the follow-up was, what's an example of how a data scientist actually pulls down a feature and uses it at NerdWallet? The way they do it right now is we work with the data engineering team to generate these standard data sets that have the common features. We're lucky that most of our business critical projects have a fairly common set of features. So we just use that as part of the ETL pipe and generate these standard data sets that get published every night, right? From the data pipeline perspective, from the ML pipeline perspective, in the ML.yaml, they just point to that feature store, that feature data set, and we pull it in as part of the SageMaker training. Yeah. So we sort of centralize it in the data engineering team yet, but that probably won't scale for too much longer.
And I think you had a question.
Any other questions that you had?
A question?
It was pretty similar. I was going to ask, like, is the feature, like, pulling down the features, is that part of the training pipeline?
Yes, pulling down the features is part of the training pipeline. SageMaker makes it super easy. You define a configuration, you name an S3 prefix, and it pulls down the data at that prefix.